Swayam Prabha. Digital India. Educated India.
We learned about the length scales, things that we can see, which we cannot see. We looked at the scale of nanomaterials. We looked at the idea of porosity. We looked at the idea of crystallinity versus amorphous. We looked at some examples in each section. We looked at atomic bonding, right? And types of different types of atomic bonding. Now, the next segment of the presentation is going to be about metal organic frameworks. How many of you have heard about this term, MOFs? MOFs, okay, few of you. Any context or you just heard it random? Won the Nobel Prize in Chemistry in last year, right? So the idea is that I'll talk a bit about MOFs to tell what they are, and then I'll tell a bit about the Nobel Prize story, how the people who won the Nobel Prize got the Nobel Prize. So the next section is essentially going to be about MOFs. And before I jump into it, this is an image that if you go to the website of nobelprize.org, this is a website. This is an image that they've put up for explaining what the field of MOFs is, right? So anyone has any thoughts or suggestions what this is or what this represents? Yeah.
So what I think it is metal organic frameworks is basically you have a giant molecule that is very porous in our definition, and within that molecule we can put in many other smaller gas molecules, and it occupies a larger space. So basically it becomes a bag of smaller molecules.
Okay.
You can expand as you input more molecules.
Okay. Any others? Any other suggestions to what this image represents? Yeah. Right. Right. Yeah. But what does a specific image represent?
So the house represents the giant molecules,
Yeah.
spaces, and the yellow things are the gases.
Yeah. So basically, you have got a home or a house, right? Which is this entire structure of metal organic framework. The structure is essentially very organized. You don't see anything that is flappy. Everything looks pretty rigid and smooth. You have got gas molecules. So there is a entrance. A gas molecule is entering the house. They're doing different functions. One of them is just sleeping. The other one is having coffee or food. One of them is reading a book. Everyone goes and does different functions. So this is this idea of metal organic frameworks that you have, every one of you said the right answer. It has got a lot of empty space porosity. It has a well-defined architecture and guest molecules. Guest molecules essentially can go inside that empty space and carry out different functions, right? So in terms of chemistry intuition, it is typically called as a self-assembly of organic ligands and metal ions. The name is very intuitive, right? It is a metal organic framework. So it comprises of a metal ion, it comprises of an organic linker. So a linker essentially will have two nodes or it can have multiple nodes, more than two nodes, to connect the two metal ions. And typically this synthesis is carried out in the presence of solvents. So the solvent molecules function as the guest molecule and they occupy this empty space. Now there are a couple of things to remember over here. This is a self-assembly of an organic ligand and metal. So what kind of bonding do you expect happens over here? This is a metal cation and this is an organic ligand. So I'll give you an example of an organic ligand. So I've got pyridine and the nitrogen has lone pairs. These lone pairs interact with the metal cation. So what kind of bonding is this? Coordinate bonding, right? So metal organic frameworks are also called as porous coordination polymers. The name is again very simple, right? There is a coordination bond happening. It is a polymeric architecture. It is not an isolated molecule and it has got porosity. So that's why it is called as a porous coordination polymer. And this is one of the examples of how the bonding works. You have got an organic entity that has excess electrons that are donated to the metal cations. Metal cations essentially will be electron deficient. They are able to accept that and that forms this coordinate bonding. So in terms of atomic bonding types we saw, this is an example of a coordination bond. And metal organic frameworks, the fundamental basis is the use of coordination bonding. But in terms of architecture, there are a couple of things to remember. The metal ions are very directional, right? Every metal ion will have only specific geometries allowed. You can either have 6 coordinate, you can have 4 coordinate, you can have 8 coordinate, 10 coordinate, something coordinate. So it will have a very specific direction. So the geometry of a metal organic framework comes from metal ion. It kind of gives a direction. And the linker also has to be symmetric. You cannot have a linker that looks, one of the edges is over here, the other edges is over here, and you can expect a very symmetric architecture to form. For this kind of architecture to form, the linker has to be linear donor, right? So this group has to be completely linear. It has to be at 180 degrees with respect to each other. If this is at this particular angle donation, you wouldn't get this structure. So the organic ligand also plays a role, but the main direction or the foundational architecture comes from the metal ion and the coordination geometry that the metal ion carries. And because this synthesis is typically carried out in the presence of solvents, you can use any solvent. It could be polar solvents, non-polar solvents, water, methanol, benzene, anything that occupies this empty space. And this is the building unit. Essentially what it forms is a three-dimensional architecture. So you can use this entity, grow it in 3 different axes, and you start having channels now. And again, it is a very simple way to construct it. You kind of construct this gigantic system using very simple building units. Any examples in the real world where you see something similar, a similar architecture? You can just think of, sorry? So, apartment, yeah, wonderful. Yeah, we are kind of living in this or staying in this kind of architecture. Any other examples? So if you go around Chennai, there is a lot of construction happening, right? You see something like a scaffolding arrangement. So when you look at a scaffolding arrangement, the pillars that go around can be the organic ligand, and the corners where they meet can be the metal ion. Or you can imagine it to be. It's not like it's the exactly same replica, but it is kind of an imagination that translates from this scale to the atomic scale. And essentially, this is something that all of us can visualize. And we need empty space in the scaffolding arrangement for a person to go up and down, move freely. Now, essentially, this is the same idea which a morph has, that a guest molecule should be able to freely move around in a predefined architecture. So this is this holistic idea of what a metal organic framework is. But someone pointed out very correctly is morphs have a lot of porosity. We looked at the idea of porosity, but just to give a context of how much porosity there is. So football was something that we looked at from the length scale. Now this is a football pitch. Anyone has a loose idea or rough idea of what is the surface area of a football pitch? Or what FIFA defines to be a professional football pitch? Any number is fine. We're not looking for an accurate number. Sorry? 120. Okay, we have got a rectangle. So 120 is which side? You can be approximate, that's fine. 100, let's say, okay, let's say we have got 100, and what is this side? 60? Okay, so the correct answer, if you go to FIFA's website, is 7140. So it's roughly something like 108 into some 70. I forgot the exact number, but it's somewhere in this ballpark region. So now if you multiply this, you get an approximate surface area of 7,000 meters square. Now to put this idea of porosity in morphs into context, is this entire surface area is present in 1 gram of material. Now just hold on to this thought for a second. The entire surface area of a football stadium, which is roughly 7,000 meters square, there is a metal organic framework that is known in the literature, which is called as DUT60. Don't worry about the name at the moment, but this particular metal organic framework has a surface area of 7,800 meters square in 1 gram of the material. Now what is 1 gram? Anyone can contextualize what 1 gram is? We just had tea and coffee now, right? We had some sugar. So if you go out to have sugar and you get a sugar sachet, this sugar sachet is essentially 5 grams. So 1/5 of the weight of this sachet will contain the surface area equivalent to a football stadium. Now just imagine this for a second. Like this is, yeah, it takes a while to absorb this idea. Not absorb this idea, right? We kind of have the entire surface area of a football pitch put into 1 gram of the material. This is, of course, the limit. Not all the morphs are going to be this porous or having so much surface area, but this is kind of the limit at the moment. Yeah.
When you say pore surface area,
Yeah.
which area are you talking
We are talking about the internal surface area. So this is the internal surface area that is present. We're not counting the external surface area. So in the Rubik cube, what we had, if you make everything hollow, what is the surface area that is inside? So this is the internal surface area that we are talking about, right? This is just to give an idea about the context. It is not like this will be equivalent to that in the perfect sense of it. Yeah. The bonds, that is why we talked about the bonding strengths, right? So coordination bonding is one of the kind of the stronger bonds that we have. If you make a system with an ionic bonding or maybe a non-covalent interaction, hydrogen bonding, that system is very easy to collapse if you have got a lot of porosity. But I agree with you, if you compare zeolites versus MOFs, zeolites are more chemically stable because they have got much stronger bonds and the porosity is much lesser. Whereas in the case of MOFs, if you do a direct comparison with MOFs and zeolites, MOFs are typically less stable, chemically less stable, but the more attractive feature is the ability to access a lot of surface area. And I'll demonstrate the reason why we need to access all of these surface areas, right? Okay, so in terms of chemistry intuition, all of you are now learning about chemistry and bonding and all of that. Anything that rings a bell with this diagram? What kind of structure is this? It is basically a metal and an acetate, right? So it is kind of a coordinate bond. It has got essentially it is kind of having this coordination bonding where the electron is delocalized in this carboxylate and it is forming a paddle wheel unit. It is this kind of representation is called as a paddle wheel unit where you have got two metals which are connected by 4 carboxylates, and these 4 carboxylates are kind of ionic ligands or ionic groups, whereas the L that is represented over here is the neutral part. So I'm using a metal that has got +2 charge. A carboxylate will have a -1 charge. So now total charge on this is +4. I've got 2 metals. There are 4 carboxylates that make it electronically neutral. So the L groups over here are essentially electronically neutral ligands. So forget about the nomenclature and the details about it, but let's say this metal has got 5 connections. So it has got a coordination number of 5. It is connected to 5 different atoms, 4 oxygens and 1 L group. This metal is also connected in the same way. Now what people thought when they were started to work with MOFs is instead of this, can we just replicate this in multiple ways? So for example, can we have this paddle wheel unit here as well as here? Instead of this R group that is at the moment focusing only on one carboxylate, can we attach another carboxylate here and then ensure that it connects to another metal? By this, we start expanding this into a polymeric network, right? This metal can further go and have another carboxylate, so this kind of expands in this direction. If you expand this in all the 4 directions, you're going to form a 2-dimensional layer, right? And again, for the case of L, instead of L being connected only to one metal, can you make L connect to 2 metals? If you start connecting L to 2 metals, you're now going to have growth in the 3rd axis also. So you have a 2-dimensional layer that forms with this metal carboxylate, and the growth in the 3rd axis is now connected by this L, right? And this is what people started working on, and they came up with this idea, which is called as a pillar layered MOF. So you have a layer of metal carboxylates, you have a pillar that connects it. So the L group in this one is this moiety that has got 2 nitrogens that connect it in this direction as well as in the downward direction. You have got the zinc carboxylate that forms this 2-dimensional layer. Now to show you the crystal structure of this, it looks something like this. So the green part in this is the carboxylate, which is this unit. The blue part is this nitrogen donor group, which is in the which is kind of connecting the 2 layers, and the metal is now shown in this particular geometry. Because this metal is a paddle wheel unit, it is not shown as an individual cation, it is shown as a cluster. So you have got the green and the oranges forming one 2-dimensional layer, and the blue parts connecting each of those 2-dimensional layers. And you start forming this empty space. It looks very similar to the geometry that we saw here, right? Something like this. It kind of forms this particular architecture, where one of the 2-dimensional layers is the zinc carboxylate, and the 3rd one is kind of connected by this DAPCO unit. right? In terms of applications, why are they so popular at the moment and why they won the Nobel Prize in the first place is because they kind of have a lot of applications. So for example, one of the answers that I got about MOFs was they have a lot of empty space and they can trap a lot of gas molecules. So this is the first application where people have started using it as gas storage systems. You can pump in a lot of gas molecules. A very good example is acetylene. You've moved around in the chemistry building, you would have seen a lot of cylinders or some cylinders lying around, right? So the idea is, instead of having those physical cylinders, can we pump in a lot of gas molecules inside these systems and then use this as solid powders to transport these gas molecules? So for example, hydrogen, acetylene, which are more toxic gases, can we just pump it into solid powders of this system and then transport it, and then depending upon the condition, we can just release it back for the application that we require. The other application is separation. Because we are able to tune the organic component, we can actually start separating molecules. Let's say we had this example of helium versus argon, right? One of them is going to have a different diameter compared to the other. Can we make the size of the pores in such a way that only one gas passes through it, the other one does not pass through it? So this is a very good example for separation. We can also use them as sensors. So typically, a lot of people working in the MOF domain are at the moment focusing on sensing applications. Let's say we are in this particular room, we are exhaling a lot of CO2. Can we make a MOF sensor? The moment there is a CO2 concentration that goes above a certain threshold, it kind of gives an alarm. Can we make that? In principle, yes. There are people working on that direction. Catalysis is one application which zeolites do. It is again something which MOFs can do as well, because we have got two components. One of them is the metal component, one of them is the organic component. We can do the catalysis from both the components. And of course, people have been using them for conductivity, electronic conductivity, proton conductivity, and even like bulky atoms for conduction purposes, right? So these are all the different applications, and there is a great interest in this area. One of the main reasons is this field was kind of introduced in the 1990s. We are kind of in 2026, and there are more than 1 lakh crystal structures that are already known. This is all man-made. People have been working on this, and they have been able to produce more than 1 lakh crystal structures of these systems. All of them very different from one another. Now, we talked about densities at the beginning of the presentation, right? What is the density of water at room temperature? Roughly 1 gram per centimeter cube, right? Look at the density of a MOF. It is 0.1 gram per centimeter cube. Because of that high porosity, we are losing out on the density, but with low densities, we are able to have greater coverage. Now, let me put this into context. We have got 1 gram of a material, let's say iron oxide, I'll write it here. I've got 1 gram of iron oxide, which has got a very high density. Now, I need to cover this particular blackboard. Let's say I'm able to use 1 gram of iron oxide to cover this entire screen. With the help of a MOF, how much do you think I would need? Which has got very low density. Let's say this has got a density of 2 grams per centimeter cube. This one has got a density of 1 gram per centimeter cube. And I have to fill the solid powders of both of them across this screen. To fill this up, I need 1 gram of iron oxide. How much of MOF do I need? Is it going to be more than 1, less than 1? Less than 1, more than 1? Anyone? Less than 1? Okay, so I'm going to require less than 1 gram of 1 gram of the MOF material, right? So this is also this overall idea that we are not actually losing out on porosity. We are actually using the benefit of porosity and the density for certain applications. And just hold on to this thought, because I'll come back to this number in a few seconds. The other thing to note is, yeah.
So you talk about slow density of being 0.12
Yeah.
But what I was thinking was, we kept it normally in air, won't that slipped it away?
Yeah. So these are some practical problems. You're absolutely right about it. So what people try to do is essentially try and form composites. If you are using it as solid substrates for certain applications, let's say we are using it for catalysis, we cannot let it sit idle. Otherwise, it will start flowing with the fluid of interest or the gas of interest. So what we typically do is form membranes out of it, and then hold on to those membranes. The membranes could be similar to what you see in any filtration device. Let's say you have got the air purifiers, right? Air purifiers have got these membrane filters. So can we form membranes of these MOF materials so that we take the benefit of the porosity and the applicability, and then still be able to put it. But you're absolutely right in terms of thought. So in terms of interest, right, I said this was introduced in the 1990s. Look at the number of publications that came out in the 1990s. Hardly anything. But look at the number of publications that are coming in the last few years. There are more than 10,000 research papers that are coming out of on this particular topic in the last 4 or 5 years. 10,000 globally. That roughly translates to more than 30 per day, right? So essentially there is a lot of interest happening in this area, and it is a very good time to explore this area, especially after the Nobel Prize have been awarded last year. In terms of organic ligands, now some of you are already studying chemistry, organic chemistry, basic organic chemistry. These are some of the very popular organic ligands that have been used for preparing MOFs. I don't want to discuss a lot about how they are prepared and what their suitability is, but one thing that I want to touch upon is the idea of symmetry, right? I touched upon this idea that the organic ligand also has to be symmetric. In this particular group, the carboxylate is the donor site. In this particular case, carboxylate, in this case, phosphonic acid, in this case, the nitrogen of the pyridine, in this case, this azolate group, the nitrogens that are part of here. Look at the geometries. This is kind of linear donor, 120 degrees apart from each other. This one is not exactly linear, but it's kind of having a symmetric nature to it. This one also has a symmetric nature to it. So to form a metal organic framework which has got some stability and some kind of long range architectures, the organic ligands have to be very symmetric in nature. And you might be wondering, how do we synthesize it in the labs? It is a man-made material, right? So how do we synthesize it in the labs? You can essentially use any of the conventional synthesis techniques. You can even use it, use to cook them in a microwave. The same kind of microwaves that we use to cook our food. Of course, we don't use the same device. There is a slightly different variant of it, but you can use any of the synthesis methods. Even you can prepare it at room temperature. There have been some MOFs that have been prepared at room temperature by certain conditions of slow crystallization, slow evaporation, all of that. You can use microwave heating, you can use mechanochemistry. Mechanochemistry is very similar to how you would prepare masala at home. You put all the spices together, you churn it into a kind of a hand ball mill. But instead of using the hand variant, this is kind of the more mechanized version. It is a ball mill that is commercialized. You can use sonochemistry, using sound waves to produce the reaction. So all of these synthesis methods are very, very common. Because the field of MOFs has evolved from the field of zeolites, people working in the zeolites have used autoclaves to prepare these materials. Basically, autoclaves are pressure bombs. You essentially put all your constituents into a vessel, a Teflon vessel, cook it at very high temperatures above the boiling point of the solvent, and then slowly cool it down to form the crystals. So the same technique has been used to prepare metal organic frameworks also. So in terms of synthesis, in terms of choosing the building blocks, not too complicated. The other thing that I forgot to mention about the building blocks is we kind of discuss about the building, right? Building being a good analogy for a MOF. But in the case of buildings, we need the pillar to start from the foundation to go to the roof. It is kind of the long length, right? But in the case of MOF, basically you're using the building unit to be this small to form a very long range architecture. And that is held by coordination bonding. So if you're able to choose the right building blocks, you will be able to form a long range material, and you don't have to complicate yourself by making fancy organic molecules that have got very long lengths and have got complicated geometries. You can choose a small building block, you can choose the right metal cation, and you can form them and form a long range architecture. Yeah.
So since all the MOFs which ligands which we saw are aromatic, the lone site in the carboxylate group
Yeah.
can participate in the synthesis. So
Yeah.
the coordination compound might not be formed.
No, so typically in this case, because this is all aromatic systems, right? The aromaticity has to be maintained. So all of these rings will kind of ensure that the aromatic nature is not lost. You're right about the delocalization of the electrons happening, but the coordination bond will ensure that the delocalization is restricted. It kind of forms the coordination bonding, and the backbone will have internal delocalization, but the coordination bond will keep happening. This is just the building unit. So the group that binds is not going to be the carboxylic acid, but it's going to be the carboxylate, right? So this has got R, this has got R. So it's going to be connected through the carboxylate, not the carboxylic acid. So the moment we form this negative charge on the oxygen, that will help bind to the metal, and the remaining part will be part of the backbone. Yeah. Okay. So in terms of classification, all of us are using the 5G phones or 5G SIM cards, right? MOFs have their classification as well. So this field evolved in 1990s. they had 1G, 2G, and 3G essentially, if you like. So first generation of MOFs is architectures where you have a guest molecule during the synthesis that occupies this empty space. The guest molecule is shown in this pink balls. The moment you try and remove those pink balls, this house of cards collapses. Basically, these bonds are weak, they kind of collapse. So this is the first generation of MOFs. The second generation of MOFs is very stable MOFs. Basically, you remove the guest molecules, nothing happens to the architecture stays intact. You put the guest molecules back inside, they occupy the empty space completely. The third generation of MOFs are essentially very fascinating. You remove the guest molecules, they tend to change their shape. They kind of are adaptive systems. The moment you put the guest molecules back, they go back to their original phase or original shape. So this is kind of the three generations of MOFs which are known in the literature. There are people proposing the fourth generation of MOFs where you have two functions in the same material or in the same crystal is what people are suggesting, but nothing is out yet. So it is kind of restricted only to three generations at the moment. In terms of the fascination, I said that zeolites are naturally formed systems. Even though you can make it in the labs, there is a limit to where you can go. With the case of MOFs, there is absolutely no limitation, right? You can choose any metal in the periodic table. You can use any organic ligand that you can think of or prepare in the labs, and you can form a framework material. Now, here is a very good example. These are dicarboxylate systems. You start with one phenyl ring, you go to two phenyl rings, you go to three phenyl rings. Essentially what happens, if the donor groups are linear, the carboxylates are linear to each other, you essentially form the same architecture. And the yellow sphere here represents the porosity. So essentially you're able to form the same kind of architecture with increasing porosity. And that is the simple function of changing the linker length. You have got one phenyl ring, two phenyl ring, three phenyl rings. So if you're able to control all of that, you're able to form an isoreticular morph. So the idea of this being the same geometries, increasing porosity or increasing access to the voids. Right? So this is again something which is very specific and common to morphs. Yeah.
So this as this porosity increases, oxygen gas or any other gas can be
Right.
can be go inside. So to maintain what we put inside, then we should seal it in vacuum continuously.
Right. So the idea is that's why we need to evacuate the systems. The original phase, whatever we form, will always have something in it. So we need to evacuate it. Once we evacuate it under vacuum, or you rightly said that either by some temperature or under vacuum, we access this empty space. Once we are able to have this empty space, we can put it into an application. It could be gas storage, separation, it could be ion conduction, anything. So basically, we need to access this phase. And the classification is all based on what happens to this phase. So if the first case, the phase completely collapses, the second one, it stays rigid, the third one, it changes its forms. So this is kind of the idea that the more porosity that we get, we should be able to access all of it. Right? Yeah.
So how is third generation any better than second generation?
So the third generation is useful because we are able to kind of distinguish between these two. So the more you learn about how to characterize this, basically if you have a signature, let's say I have got a signature for the first phase, let's say I've got a peak in an X-ray diffraction, right? If I carry out the X-ray diffraction, I get a peak corresponding to the first phase. Now I have a X-ray diffraction for the second phase and it looks something like this. So the moment I'm able to access this, I'm able to see the changes that are happening and I can confirm for sure say that this is the confirmed phase. Whereas in this case, I may not be able to say from X-ray diffraction because the peaks corresponding to both the phases will be exactly the same. So this is kind of useful in a lot of characterization techniques. And it can also be useful to have some applications also. I'll touch upon this in a few slides. Okay, so these are the three people who won the Nobel Prize last year. Umar Yagi from USA, Susumu Kitagawa from Japan, and Richard Robson from Australia. And all of them kind of won it for three different reasons. So if you look at the three publications that they produced, the key publications that won them the Nobel Prize, Robson's paper came out in 1989, Yagi's paper in 1995, and Kitagawa's paper in 1997. And the key thing to highlight over here is all of them actually did work on three different areas of morphs. So Robson was the one who proposed that you can create a coordination polymer which has got empty space. So his contribution is kind of attributed for the creation of the idea of metal organic frameworks. What Yagi did is essentially prepare the second generation of morphs to stabilize the morphs. So the morphs that Robson produced were not very stable in air and moisture, but the morphs that Yagi produced are now fairly stable. And what Kitagawa suggested is, why do we even make them? We should have some benefit out of it. So what he suggested is we can start utilizing this empty space for trapping gas molecules. So his main contributing paper came with this idea that can we use the cavities for trapping small molecules. So the way I see it, or any young researcher in this field sees it, is Robson suggested that we can create pores, Yagi said that we can stabilize them, and Kitagawa showed that we can utilize them, is how these three areas or domains have been there. But the main question arises, like for any topic or any field to arrive, it didn't happen overnight or it didn't happen in a few years. It took a while for it to arrive. So if you go back in history, I think all of you will learn about this particular gentleman, which is Alfred Werner. He's regarded as the father of coordination chemistry. And he initially proposed that if you take a cobalt salt, a cobalt tetra-ammonium dichloro system, essentially it looks something like this. And the main idea behind his hypothesis was if you take cobalt, it will have a 6 coordination geometry. The 6 coordination geometry will look exactly like an octahedra. It will not have any random geometry. It will have a very specific geometry. And this is why he's regarded as one of the most important persons in the discovery of morphs also, if you go back in time, because he proposed that if you take a metal cation, it will have very specific directions of binding. He didn't make a morph, he didn't make a polymer, he just made a simple salt. But at that time, there was no information known about how this bonding works. So he kind of proposed that this is how the bonding works in small systems. So he won the Nobel Prize for this discovery in 1913, more than 100 years ago. But the Nobel Prize of 2025 kind of attributed his contribution with this sentence, that his contribution gave a predictable joinery method in structure design. So if you are able to identify how the building blocks connect to each other, you can actually start predicting the geometries in the longer range. It's a very elegant way of looking at it, but his discovery is also very important. The other example that is very important in the discovery of morphs is this idea of Prussian blue. We are in Tamil Nadu, right? So Tamil Nadu is a state that is known for the dye industry or the textile industry. Prussian blue is one of the more important dyes that were discovered like late in the 18th century. But we didn't have X-ray diffraction techniques, so we didn't know the crystal structure of this. Only in the 1936, in this particular publication, was the crystal structure of this system known. It is a very simple molecule. It has got iron, carbon and nitrogen, just 3 atoms. But iron is present in 2 oxidation state. It has got a +2 oxidation state. It has got a +3 oxidation state. And we form this architecture. It's a 3-dimensional architecture, alternating sequences of iron +2 and +3 connected by carbon and nitrogen. But it kind of looks very similar to a morph, right? It has got 3-dimensional architecture. It has got voids in between. It has got a channel that essentially makes it like a 3-dimensional architecture with porosity. It doesn't have a lot of porosity, but it still has that idea. So what the Nobel Prize citation for last year said, that if once we knew that Prussian blue structure looks something like this, it is now possible to design and produce such cavity forming structures and to control the inclusion of small molecules within them. Very elegant, right? We had Werner suggesting that the geometry is predefined for a specific metal cation. If you understand the geometry, we can produce a long range architecture. And Prussian blue kind of amplifies this. It says that if you have got porosity or a cavity within it, we can actually start filling small molecules inside that. Now remember the year, this is in 1936, when in that Nature paper, when it was suggested that this is the crystal structure. If you turn back the history pages, you find one fascinating paper in 1916. It is a paper that came from a group in Japan. It is a paper written in Japanese, but the term coordination polymer was first proposed in 1916. So the idea of forming a polymer using coordination bonds was proposed in 1916. But there are a few more examples, specifically in the 1950s and 60s, where people started using this idea. So you take an organic molecule that has got nitrogen groups at the terminal site, you treat it with copper nitrate, and you form this crystal structure. Now this crystal structure is a 2-dimensional cross section. Essentially this is a 3-dimensional architecture again, but this is a 2-dimensional cross section. It has got empty space, it looks very symmetric, and it forms this 3-dimensional periodic structure. Very morph-like structure. But again, at that time, the people were not interested in analyzing this to a great extent. They were more interested in understanding the binding tendencies. So this is again a very good example for the foundation step or formative steps for the development of MOFs. Another paper that came in the 1960s, again the same idea. You take copper nitrate, you take a different organic ligand. Instead of urea, you take thiourea. You just replace the oxygen with sulfur, and then you kind of form this architecture that has similar features as a coordination polymer. So there were hints that were coming that you can form coordination polymers, you can have porosity as described by Prussian blue, but nothing happened for a while until these guys came in. So now what I'll do is I'll describe a bit about their stories. Some of the stories are very, very inspiring for all of us, and see whether something of this links to us as well. So these are the three people who won the prize. This is the photo of how they look like now. Robson is very old, he's close to 90 years old. Yagi and Professor Kitagawa are still working. He's changed his affiliation now, he's in Berkeley, whereas Professor Kitagawa is still in Kyoto University in Japan. And Richard Robson is in Melbourne in Australia, right? The one thing that links all of them is this passion for doing something creative. So Richard Robson was working at University of Melbourne. He was a young professor. His head of the department at that time told him that the way they teach atomic models to students like you has to be changed. It is very outdated. So what he did, he went to the workshop. Every university or department has a workshop. So he went to the workshop, he started collecting wooden models to demonstrate how atomic modeling works. So in the examples that we saw in the morning, essentially what we are looking at is an atomic bond between A1 and A2. Now when he came back, he started teaching to his students and all of that. When he came back from his lectures, he used to imagine, what happens if I have one molecule, I have got another molecule, can I use the same binding principles to connect two molecules instead of two atoms? And this is a thought that stuck with him for a while. It didn't happen very quickly. Then he gave this idea to one of his students. It took about roughly 10 years for him to take his idea from just the idea to practice. He gave it to his students, and then 10 years later, the paper in 1989 came about. So essentially, they just put this idea that we have a metal cation or a metal cluster, we've got an organic ligand, and we have got another metal cluster. One molecule, one entire molecule, can we connect them together? Instead of just connecting atoms together, can we start connecting molecules together? So this is this underlying thought that gave rise to the field of MOFs in essence. Yagi's story is very different. So he was born in the country of Jordan. Jordan wasn't the most developed country at that time. They didn't have access to electricity, water, and all of that. So he kind of didn't know about chemistry much. The only time he saw chemistry structures was in a textbook in his school library. His father sent him to the USA at the age of 15 to have better education, to learn more. He didn't know English at the time, and he was in New York. So that was a bit of a struggle for him. But when he started his professional career, his dream was, he started his career in 1992 as a young professor. His dream was that he should make one research breakthrough. And look at him now, he has got a Nobel Prize. His research group has made several breakthroughs. So the idea from he started his career in 1992, he won the Nobel Prize in 2025. So winning a Nobel Prize is not that easy. It takes a lot of years, but it takes a lot of effort as well. And that is kind of the underlying message from his story. So Professor Kitagawa is having a different story in itself. He was an established professor when he entered this field. And one of the things that he says is very close to his heart is this idea, or is this philosophy, the usefulness of useless. So when he started proposing about the utility of MOFs, a lot of people kind of ridiculed him. They said that this is stupid, that these materials are unstable, they kind of break or collapse, and there is nothing great about them. We don't believe that these materials will ever be useful. So he kind of stuck to this idea that we are creating useless materials, but there is some usefulness in that. And he kind of kept going on and on. And one of the key things that he kind of appreciates and tells everyone is that when you're working on challenges or research problems that are way bigger than routine, you need to have teamwork and cooperative skills. And the idea of cooperative kind of comes from the materials that we are looking at. There's a cooperation between the ligand and the metal, and it forms this long-range architecture. So the idea that if you have good teamwork and cooperation skills, we are able to form something bigger than the individual blocks. So this is kind of his underlying thought and philosophy of how we can make MOFs and how we can make great scientific discoveries. So this is one area about the past, but now we are living in 2026, and what happens to the applications, right? I've shown a few examples of the applications, but what happens in principle when we start applying them in the real world? You might ask that, are they even used at the moment? So one of the answers is yes. This is a company based in Canada. It's called Swante. What they have done is something to answer your question, is they have made membranes out of MOFs. So they have taken MOFs as powders and they've coated it with something. They've made membranes out of it. And what they've done is they've put them at the exhaust of flue gases. So flue gases are industrial exhausts that typically come from manufacturing sector. The example that they're looking for here is the industry that produce or makes concrete. So the exhaust that comes out from it has a mixture of carbon dioxide and nitrogen. They have made a particular MOF structure that is able to bind selectively to carbon dioxide and it lets nitrogen go. So you can imagine that a factory exhaust is coming out. You have a membrane of the MOF. It lets out nitrogen. It traps CO2. And this particular membrane is like a cartridge. Once it gets fully filled, you can remove this cartridge. You can put the next one. And you can use this cartridge. Now you've got concentrated CO2. You can liquefy or pressurize this CO2 to either put it under the ground geothermally, or you can just use it for some applications. You can catalytically convert CO2 into methanol or some value-added products. So essentially, the idea of trapping or concentrating CO2 can be done by one of these materials. And one of their partners, which is a big chemical company called as BASF, is producing the MOFs for them. So they are able to produce MOFs in bottles and even in ton scale, and they're sending these materials to Canada to produce these membranes. And one of the announcements from the CEO last year is they want to make a gigafactory for carbon capture. So gigafactory would be something where they capture gigatons of carbon dioxide in the exhaust. And then you can use essentially to trap all of that CO2 and clean the air. So this is a project at the moment ongoing. So this is something which is very fresh, right? This was May last year. So this is something very exciting. And if the results get through, we might have a breakthrough of using MOFs in some of these applications. One of the other cool applications is this idea of water harvesting. So this is a work done by Professor Yagi's group, the one who won the Nobel Prize. Essentially, the idea is you've got a porous material, something like a silica gel now, right? You put this material in a desert-like region. Let's say you put it in Rajasthan. During the night, when the temperatures drop, when it starts to have higher humidity, the MOF is able to start absorbing all the water from air because it is able to function at different humidities. So at night, it starts to absorb moisture. Then you close the chamber. During the day, when the sun comes out, the temperature increases, the trapped moisture can go up and condense, and it kind of collect as liquid water. And you can use this liquid water directly, or you can purify it and use it for further applications. So essentially, you can use this as a repeating cycle to trap atmospheric moisture. And this is particularly relevant for regions that have got very low groundwater. So desert-like regions are perfect for this. And you might ask, then why not silica gel, right? Silica gel is also doing the same purpose. The problem with silica gel is the regeneration. To remove the moisture that gets trapped into the silica, we need to input more energy. Whereas if you have MOFs, sunlight is itself enough to remove all the moisture that comes in. And you can use the material for the second cycle or subsequent cycles also. The other application where I was touching upon with the idea of density is this cool example that came out from a group in USA. So you might have heard about some chemical weapons being used in Syria and other places, right? So the US Army gave a project to one of the research groups to design army suits made up of MOFs. So what the idea was that this is a toxic molecule, which is one of the nerve agents or a chemical weapon if you like. You just have the MOFs created jackets. So the US Army personnel are out on the field. They have got these jackets on. Once this comes in contact with the MOF, essentially it gets catalytically changed to a non-toxic species. I'm not discussing the catalytic cycle at the moment, but this kind of gets catalytically cycled to a non-toxic species. And then the army personnel can still work in that area without compromising their health or safety. And this is a project that was later done by a company called as NewMat, and they are now kind of working on other kinds of pollutants. So PFAS is something which is another pollutant that they're looking at by using some vest or some jackets which people can wear. So we are all living in this age of AI, right? And MOFs are not too far from it. So at the moment, what people are doing is essentially digitizing all the data that is produced in the labs. So in the olden times, people would, or you, when you work in the lab, you will all write your observations, you will write a conclusions, and then make a story out of it. But now what people do is essentially translate or digitize all that data and essentially convert it into a morph GPT. Essentially don't have to look at chat GPT, but we can have morph GPT. So the idea here is, if I want to make a morph for CO2 capture, I don't have to use my brains anymore. I just give it to morph GPT, it tells me what morph will work for it. I tell it this is the condition, I have to make it work in Chennai, which has got high humidity, high temperatures. Give me a morph that works over here. It can produce an output within few seconds. Go back to the lab, produce the morph, and test it out. So this is where the field is headed next, where we essentially have a large library of molecules and materials. We just input it into the database, we put in a command, and we get the output out of it, right? So this is living in the age of AI. Now, this field, as I showed at the beginning, has got a lot of interest and a lot of people working on it. So if you're interested, you can go to this link. Basically, this is a pin of every research group that is working in the world in the area of morphs. So this is a project done by one of the researchers in Germany. They've kind of curated all the information of people working in the area of morphs across the world. And you can see that there is a pin on every place. The one spot that you will see here is a sign of like a death sign. So this was given to Professor Stoddart, who was a Nobel laureate in 2016. He worked on the field of molecular machines, and he passed away there. So that's why you have this particular symbol. But the other pins are people still actively working in this area. There is an Indian map of that. If you take out the Indian version of it, these are some of the people who are working in this area. So if you encounter any of these researchers or scientists at some conferences or some meeting, there are different people working in different areas. Of course, in Chennai, my group is working. There are a couple of other people in IIT Madras also who are working in this area. But this is kind of the Indian map, and you can see that a lot of states have got people now working in this area. So the main application that we are looking at is water harvesting. So we need someone working in Rajasthan also now, so that we cover that aspect as well. Good. So with this, I conclude my presentation on the domain of morphs, but I'm happy to answer any questions or queries that you might have. If there is any further interest, please do contact me after this. I'm here in this building, so during your time over here, if you have any other questions or any other thoughts that come to your mind, please feel free to reach out. Yeah. Morphs are expensive, but at the moment the expensive part is the production of the organic ligand on that scale, because the metal salts we essentially have there for a lot of other things. The production of the organic ligand is expensive. So what people are trying to do is trying to produce them in a more greener and more cost-effective manner. But that, I think, is a more engineering problem than a chemistry problem. If you are able to make the processes more cheaper, we'll be able to produce them at much lower prices.
Right now, what is the most effective way to synthesize?
For the synthesis of morphs, the most elegant way or people have tried is the autoclave method or the solvothermal method, where typically what we do is we essentially have a vessel where we put the metal salts, we put the ligands, and we put the solvents. We put them together, we seal it up, we put it into a pressure bomb. The pressure bomb is there to ensure that there is good pressure on the system, and we take the setup and heat it at a much higher temperature. So essentially we put it at a temperature beyond the boiling point of the solvent so that there is enough pressure that creates, and then we do slow cooling. The idea of slow cooling is to essentially form the crystals that come out of it. So, and the other reason is we form the thermodynamically stable product. If we carry it out at a very fast condition, we are likely to get some amorphous product or some kinetically favored product also. So the idea is we use this, but this is not scalable, right? If you have to produce 1 ton of the material, this is not a very feasible option. So what people have been trying to do is, let's say, take metal as a powder, ligand as a powder, pass it through a screw extrusion method. So I wouldn't explain entirely, but this is a kind of a mechanized version of ball milling. So you pass the metal powder, you pass the ligand powder, you essentially ball mill it, and the output that comes from it is a morph powder. Yeah.
So towards which aspect is your research group working on?
Yeah, so my research group is mainly focused on sustainability. So something which you asked is trying to make the morphs more greener and synthesis more sustainable is that aspect. And in terms of application, I'm more interested into water harvesting and using them for battery applications. So trying to use them as battery electrode materials so that we are able to store charge, have greater inclusion of charge. Because of the porosity, we can include higher amount of charged species there. 3D printing, yes. People are trying that, but I don't have a good answer for it at the moment in terms of the success rate. But people are trying in that area also. Yeah.
So one of the applications of MOS was storage.
You're right.
So instead of synthesizing something as expensive as this, wouldn't I be better off storing gases at high pressure in a cylinder instead?
Right, right. So the main problem comes from safety aspects, because if you're storing it in a high pressure cylinder, essentially if you just physically move it around, you're more likely to break it. So in terms of safety considerations, you have to ensure that there is a proper cylinder, there is a chain around it. But these are essentially packed in bottles. You can just move bottles around. You might have the same amount of gas that is loaded over here with less safety issues. That is the overarching idea. For example, if you want to use them in vehicles, like let's say hydrogen might be a source of energy in the future, right? So if you want to pump in hydrogen in a cylinder, you cannot carry a cylinder in your bike or vehicle. Instead of that, you can have a small segment of a MOF powder that is laden with hydrogen, and then you can use it for some application.
So instead of having something with a very high pressure, with a lesser volume, we can store more.
Store more, exactly. Yeah. Any other questions? Yeah.
So could you explain the disposal mechanism for
Yeah. So typically, the main thing in the community at the moment is we don't want to create a plastic problem. The plastics have a lot of utility, but they have a lot of issues as well. So what people are trying to do is essentially try to have a circular economy where you manufacture something, you utilize it, you have a second life, and then you recycle it. So what people are trying to do is manufacture it in a greener manner. Utility is something which depends upon the application. Can you have a second life to it? Can you reuse it? And the last part is recycling. So for the recycling bit, MOFs, one aspect is slightly easier, is to dissociate the coordination bond. Unlike plastics, which form this long covalent architecture and it's hard to break them, so that becomes a disposal problem. But whereas in the case of MOFs, if you use building units that are much greener, people are trying to understand how the recycling works. So there is no direct answer at the moment, but what people are trying to do is try to focus a lot on second life. Can we make them use multiple times, or can we recycle them? So recycling will take some efforts, I guess, but there is good interest and effort in that direction.
But like, for the sake of the environment, like, isn't it better to first devise a proper recycling mechanism and then go to
Right. That's absolutely correct. But the problem is, until we know how to manufacture them, we cannot know how to recycle them. So the idea is like it kind of starts from here. How to make them first in the first place is the harder challenge. So that's why people who started with this have given this up, because this kind of uses a lot of solvents, and they are now focusing on solvent-free synthesis. You don't have a requirement of a solvent. So now you're kind of already helping the environment by reducing the solvent. But now what people are trying to do is, can you use different recycling methods to essentially get back the building units, get back the metal and the ligand, and form another round of it. Yeah, any other questions? Yeah.
And the second generation of MOFs,
Mhm.
meeting the same structure before and after the S molecules.
Right.
NPTEL. So does that mean that they can still be reused as many times as
Yeah.
you want?
So the idea is typically that if you have a rigid architecture, you can use it multiple times. The good example was the Swante thing. If you make this cartridge, you empty the CO2 that is concentrated, you can reuse it back into the flue stream. That is the thought, and this is what they're trying at the moment there.
So is there generally a limit to the amount of time?
Yeah, so I don't have the exact answer at the moment, but typically what we do in the lab scale is try it out for thousands of cycles. So we just put gases or solvents inside, take it out, put it back on and remove it, and see the efficiency over those 1,000 cycles. In the industrial settings, of course, it translates into a bigger problem where we have to check it at now liters versus smaller volumes in the lab scale. So we might have issues that come up there which we haven't seen it in the labs.
Said that you are going to be working on the battery.
Mhm.
Can you use these MOFs in solar panels?
Solar panels, yes, people have tried, but the conversion efficiency is not great at the moment. That is why there is less interest. The main conversion efficiency would come from the organic ligand. So if you are able to design better organic ligands, we might get a breakthrough. But then if you make better organic ligands, the cost increases. So for the solar panel, we have to compete with existing solutions. So that's one kind of the bottleneck at the moment. Yeah, any other questions? If not, feel free to reach out to me in the offices during your stay over here, And I wish you all the best for the program as well as your future as well. Yeah.
Sir, this might seem a bit controversial.
Yeah.
But not really for the science now.
Mhm.
Because if this small manufacturing, like, goes well,
Mhm.
becomes successful, it will obviously pose threat to like several other like pre-existing, well-established industries.
Mhm.
And so like they will get threatened, obviously.
Yeah, you mean in can you give me an example of
Like for example, when Nikola Tesla,
right,
like he found a way to make better energy sources.
right?
He he was obviously killed before he could make
Mhm,
achieve a
mhm.
lot of progress and like that is the way
Yeah.
things are with
Yeah, yeah,
better
yeah.
innovation.
So at the moment, the main application for MOFs is rather than competing with something, it is trying to find a solution to the problems, right? So the CO2 problem, you don't have a good solution at the moment. None of the materials are working well. So we just try out MOFs. If they work well, they are better. Battery industry is going to require a lot of materials because we need a lot of energy storage. We've got a lot of sunlight outside, but we are not able to harvest it. So can we have better batteries out of it? So this is again just a trial to see if MOFs work there. So I don't see this to be a problem with MOFs, that we are not essentially replacing anything, but we are trying to find solutions for problems that are kind of unaddressed at the moment. Yeah.
Sir, in first generation molecule
Mhm.
MOS, as you remove the gas molecules, the structure collapses,
Mhm.
right? But then how did the gas molecule provide stability to the structure?
So the gas molecules are having this non-covalent interactions, right? The hydrogen bonding interactions, the pi-pi interactions, and all of that. They're essentially able to hold the framework together.
So then how is that overdone? So then why doesn't it happen in second gen?
So second generation, the coordination bond itself is much stronger than the host gas chemistry. Yeah, if there are no more questions, then we can stop over here. Yeah, okay.
Good afternoon, everyone. Thank you, sir. Thank you for your spending valuable time and for navigating us through the nanospace from the various scales of measurement, porosity, and morph and their application. You really inspired us, sir, to explore nano world. Moreover, coincidentally, you are the one who interviewed me. And thank you, sir. Thank you once again for your eye-opening session. Sir.